right, everyone. Really excited to be hosting the Fireside Chat. So remote sensing, such as satellite imagery, has produced an increasing rich source of global data with numerous applications in clean energy, deforestation, poverty mapping, among many, many others. And so the format of this session will be a fireside chat with experts who are pioneering work at this intersection, including discussion on the breadth and challenges across various methodologies and applications. And with us on this panel discussion are Victoria Coleman, the CEO of Atlas AI, Rajagopal, the professor of civil and environmental engineering at Stanford, Rose Rustowicz, applied scientist at Decartes Labs, Jack Kelly, the CEO and founder of Open Climate Fix, and Grega Milcinski, the CEO of Sinergise. So I'll have each of these speakers introduce themselves and give a couple minutes of opening remarks, and then we'll dive into moderated questions. And then, of course, we would love audience questions as well. So Victoria Coleman, could you please start?
Hi, thank you, Sharon, for including me in today's conversation. Hi, everyone. My name is Victoria Coleman. I am the CEO of Atlas AI. Atlas AI is a startup that was started by 3 Stanford professors. I know at least one of my co-panelists knows them all very well. Hi, Rose. The company started about 1.5 years ago and is in the space of geospatial analytics with particular emphasis on emerging markets. Our focus is pretty kind of strictly on Africa, the continent of Africa. The core of what we do is generate insights using machine learning models in areas where there's little data to start with. So we chose Africa because that is a place where the data need is the greatest. It's also the place where there's very little training data to work with. So our approach has been to try and build out technologies that are effective in the absence of lots of training data. With that, back to you, Sharon.
Fantastic, thank you. Ram, would you like to go next?
Hi, Sharon. Thank you for having me here. I think it's a wonderful session. There's 2 places where we have used a lot of remote sensing. One is in the work of our lab in the electricity sector. One of our focuses has been using data optimization and new types of sensing to improve how we integrate renewables and control demand and do all kinds of large-scale deployments. A challenge to the electricity sector has been the unavailability of complete and large-scale data sets about where do we have the different generation sources, including solar, wind, traditional generators, the networks that interconnect them at the transmission and distribution level, and then a reasonable model of the demands. This absence of this data has difficulted not just the research work of scientists at Stanford and other universities, but of companies that want to develop new markets, of policymakers, and so on. So based on this challenge, we started this project at Stanford where we use remote sensing to map a lot of this infrastructure. Sharon is one of the key members of the team as well. And so far, we have had success with solar panels, but there's a lot to be done. Another place I've used remote sensing in a slightly different context has been in the agriculture sector. And there, what we found is there is a lot of need to validate what's going on in the field for different people who participate in this sector. And some students who were in my lab in the past, they took some of the things they learned from projects in energy and created a startup in Brazil that's helping the ag sector to connect better through remote sensing as being one piece of it. But I also think a very important topic that goes along with remote sensing is, given the imperfect information that you obtain from remote sensing, how can you make good decisions? So I think there is that side as well. So those are the two things that really interest me these days.
Thank you, Ram. Rose, would you like to go next?
Yeah, hi everyone, hi Sharon. It's really great to be here today. Thank you again to the organizers for bringing this community together over the last few days. My name is Rose Rustowicz, and I am an applied scientist at Decartes Labs, working at the intersection of remote sensing and machine learning image analysis. I thought that I could tell a quick story as my introduction. So this story kind of demonstrates the reason that I was initially drawn to remote sensing, and it kind of still holds for why I'm still drawn to it today. So the story goes, I was taking a tour at RIT, this is a university in Rochester, New York, to learn about the imaging science program there. And at this time I was deciding what I wanted to do for my undergraduate education, what I wanted to study. And we were in the foyer of the imaging science building. There was a huge canvas up on the wall that was showing an aerial image over Haiti that was taken after the 2010 earthquake there. And the person that was giving the tour was explaining how students and professors within the imaging science department were using these images to help with natural disaster relief after the storm for those on the ground. And so they applied these image processing algorithms to extract useful information to help these people that were in crisis. At that time, the only thing that I knew that images were any good for were looking at, like capturing memories. And I really had no idea of the power of a pixel and of this gap of information that an image can fill, especially when other sources of data, as Victoria alluded to, aren't relevant. That concept of, I find it quite fascinating that there's so many positive applications, especially here in climate change, that we can tackle with this technology and with the information that it provides. And that's what's kept me in this field from that very moment when I first decided that I wanted to study imaging science. So that's it for me. I'm really looking forward to our discussion. Thanks.
Thank you so much, Rose. That was a beautiful story. Jack, would you like to go next?
Hello, everyone. I'm Jack Kelly, and I wear two hats. So I spend half my time working at National Grid Electricity System Operator, where I apply machine learning to forecast renewables. And the other half of my time I spend on my non-profit, Open Climate Fix, where we're entirely focused on trying to forecast solar electricity power production using machine learning and satellite imagery and numerical weather predictions. So why do we want to do that? So it turns out that today, electricity grids, one of their main tasks is at every moment balancing supply with demand. So we can't store very much electricity, so at every moment supply must pretty much exactly match demand. And that's challenging with, and so if a large cloud comes along and wipes out a few hundred megawatts of solar PV power generation, then that has to be replaced very rapidly with, the way we do that is we keep lots of natural gas powered generators sort of spinning but ramped down so that they can be very quickly ramped up. And that's what we call spinning reserve. So it's literally big chunks of spinning metal that are ready to jump in and provide power if we rapidly lose power from another generation source. And that, of course, is carbon intensive and financially expensive. So if we had better forecasts, then we'd need less of this spinning reserve, which would reduce carbon emissions and reduce costs. So that's one of the reasons why we're working on trying to produce better forecasts for how much electricity is going to come from solar electricity generation, using machine learning and satellite images. Thank you.
Thanks so much, Jack. And Grega?
So hi, I'm Grega Milcinski. I'm a CEO of Sinergise. We are probably most well known for Sentinel Hub, which we started about 5 years ago when the Sentinel satellite started to give the data out. And at the time we realized that the access to the data is simply not I mean, it's not feasible for the volume of data that is available. So we started building this tool, and now we are probably most well known for a couple of things. One is that we copy all the data to Amazon. So whoever wants to use the Sentinel will probably use the archive that we copied there. Then the second thing is the EO browser, which makes it possible for just about anyone to explore the full archives of the data. And the last, the EO Learn, which is an open source machine learning library, which kind of bridges the gap between machine learning and the Earth observation. And what I find really amazing with all of this is that satellite data kind of provide an objective view of our planet, something that I think is very important, especially in today's world of fake news. Now, the satellite data really is there and anyone can access it, and really anyone. And we can see what is happening with our planet almost in real time. And I mean, we were all probably watching the deforestation in the summer, in August last year in Amazon, where things were really bad, and it was possible because of the satellite imagery, right? But now what I'm missing though is that there would be tools available that would make it possible to find these things like all across the world when they are happening, so that we can really all observe and then act on it. And this is why we are putting so much of effort into machine learning, because there's simply too much of data to look. So we need to use the help of computers to kind of comb through the data to identify things that are worth to look at. And then hopefully we realize that things are really important and then starting to work on it. Thank you.
Fantastic, thank you. So we'll start with a few moderated questions, and of course, among panelists, you can take the ball at any point, and please also feel free to ask questions amongst yourselves. So the first question is, what insights have you gained from working with remote sensing data, and what has been particularly interesting or surprising? Does anyone want to start?
You want me to go first?
Sure.
All right. So, as I was saying earlier, I think the most kind of exciting thing for us was the opportunity to work in a space where data is largely absent. And that's both, of course, a challenge and an opportunity in some ways, because if there's a lot of data on the ground already, it's kind of hard to distinguish yourself. If there's very little, then anything is better than nothing. But I think the thing that personally kind of surprised me is the accuracy really with which you can, using these techniques, these machine learning techniques, predict outcomes out of sample. That's the thing that kind of really struck me. All the way from population mapping to targeting programs to looking at deforestation, agricultural yields. The possibilities are endless. Being able to do that and support people's decision-making processes has been kind of an eye-opener for me. In the work that we do in poverty mapping, for example, in Africa, we start with a very small, relatively small kind of sample, about 25,000 data points in about 12 countries. And out of that, we're able to generate pretty accurate estimates for asset wealth for the whole continent out of sample. Every time I look at that, it kind of blows my mind, right? It's just so awesome to be able to do that and do it at what I call it standoff. You can do this amazing kind of measurement without having to have boots on the ground. Just like to finish that thought right now, that is just so important. One of the things that, of course, everybody is affected by, including us here today, is the pandemic. And of course, the pandemic has, impacts different communities differently. In Africa in particular, combined with natural disasters such as, for example, the locust infestation in Kenya, it really is pushing the country to the brink of a famine, becoming a humanitarian crisis. And one of the ways that you can, figure out if the food supply is working well or otherwise is to see whether markets are active or not. Well, how do you do that? Ordinarily, they would send people out to measure how many trucks are coming in to deliver produce in these markets. Well, now with the restrictions and the worry that people have about being next to others, they can no longer send people out to do this. So, being able to observe these things from afar and still be able to provide, really, very, very important information to decision makers is something that, I'm just so grateful that we have the technology to do today. I'll stop there.
I think from our side, maybe I can tell you the experience of how we started on this. We went to a meeting with a few utilities here in California, and one of the things in that meeting that surprised us is that they mostly don't know where the residential solar panels and commercial panels are in their own system. And this means they spend millions of dollars every day in their electricity procurement, handling uncertainty that they could very easily measure. Our students heard that question and they were saying, well, we are working with NREL and a few other organizations to send data, paper documents, and try to track this, but we're always behind. At the time, they were behind by a year or two. So 2 students heard this. They went back, and within 3 months, they had gone from nothing to having mapped all the panels in the US and an algorithm that used ideas that others had developed, but for this great purpose. And then seeing that happen, and it was so easy, showed me how far along these computer vision techniques had reached, and also showed me another effect. When we published these results in December, we optimized the algorithms in some ways. We wanted to run it again and make sure it all works. We got requests from so many people, starting with NREL, Berkeley labs, who have these programs that do the paper mappings, and they realize there's huge gaps when they do that. So just seeing the ecosystem you can generate around these solutions, for me, was the most surprising fact, and how easy it is to at least have an initial working solution. I mean, of course, to get things working to higher accuracy, it's still a challenge, and doing things like mapping distribution lines, it requires some creativity, but pretty much anybody could do this with some basic knowledge of the tools and technologies. So I think it's a big game changer for the electricity sector for sure, and others.
I can kind of add to that. I think the first thing, not totally related, is the main thing that I learned when I first started looking at remote sensing imagery is that the world does not look like Google Maps. It doesn't look like the image that's behind me. And remote sensing data is really dirty and messy and needs to be cleaned up to really make the science happen. But now going back to relating to these last 2 responses, I think, yeah, one of the other main things that I've learned is there's so many gaps in knowledge about the planet. Every time that I would start on a new project, you're just introduced to more gaps, and that really just shows the promise for what we can do with satellite imagery. Just to give an example, when I was at Stanford as a student in the AI and sustainability group, I was working on a project in food security. This feeds into some of the stuff going on at Atlas AI as well. And so in that project, we just wanted to map the crop types that were being grown in sub-Saharan Africa, such as in Ghana. And just from doing some search around like the current information that exists around that, there's really not much. The information that is collected is ground surveys that happen maybe once or twice every 10 years, and those are very limited to only a few thousand households. So again, just kind of pointing out the fact that there's this huge gap in knowledge, and we have these tools to fill those gaps.
I suppose building a bit more on what the others have said as well, I think one of the things that I find most surprising about working with especially geostationary satellite imagery is that the technology works at all. and that the data is freely available. So it just slightly blows my mind that people have figured out how to make cameras survive being strapped to tons of high explosive, launched to 36,000 kilometers above the Earth's surface, accelerated to 3 kilometers a second, and somehow we managed to get an image back every 5 minutes, and most of the images are pretty good, and we get that data completely for free. It's just bonkers. So that's, I think, one of the things that I find most surprising and I'm most grateful for.
And to follow up on that, I mean, what is for me really cool is how cheap it is to actually use these things today, due to the clouds and due to the cloud providers having this data available there simply to use without us needing to pay for the data storage. And I think this is really a huge game changer, because remote sensing data are with us for what, decades, right? 40, 50 years. But up until very, very recently, people were working with each individual scene for a couple of weeks before they actually got some results out of it, and they really looked into it. And now suddenly, like really over a few years, I would say 2 or 3 years, now we have unlimited amount of data available that anyone can, with a couple of hundreds of dollars, you can really do magic, and you can process the data on almost a global scale. And I mean, that's something that I believe provides so much of opportunity, which is not yet used, because most of the remote sensing experts, they are still used of these, let's say, semi-manual methods that simply don't scale in terms of the volume of data that is there. And I mean, yes, they have knowledge, they know what to do, but I mean, simply it's too slow. So if we now ramp up with proper machine learning, I mean, simply with statistical models, then we can find out so much more.
Fantastic. Thank you, everyone. Given the machine learning audience that is here today, I think they'd be curious to ascertain essentially what machine learning techniques you use. So if you could go over some machine learning techniques you might be using, of course, it could be just using off-the-shelf things. I think that would be really enlightening.
I'll start so that we don't go always in the same. There are lots of tools really available there, because I mean, simply because the most of the machine learning technology is built on the computer vision, and computer vision is well established because of the Facebook and all the other face detection stuff. And I mean, what I see is that most of the people start simply by using TensorFlow, which is there, and it's super cool tool. And then, I mean, what you can do is you simply throw in the data, satellite data, you throw in the labels, and then you get something out of it. But I mean, and this is also how we started, because it's simply the easiest. But then, I mean, we stepped one step back, because what the problem with this approach is that you really don't understand what's happening. So we went from the other side, and I mean, we started with a very simple random forest methods, right? I mean, the boring stuff. Yet, I mean, you get quite good results with a random forest as well, and it's usually much faster and cheaper in terms of the infrastructure, and you have a much better idea how it works. So then, I mean, and this is what I would recommend, is that, I mean, you start with simple stuff, and then you introduce the neural networks and all the other deep learning technology, because, I mean, it's there and it's really easy to use. But I mean, it's good to know which problem to tackle with which methodology. Otherwise, you simply are wasting time and resources, and you don't. I mean, you get results always. I mean, that's the nature of this field. But I mean, you could get much better or much easier results. And what I think is also important is that when we are building these things, that we do think about cost, right? Because I see many startups that are throwing lots of money into simply into the cloud resources to build stuff that, I mean, that doesn't have the value, the added value that it costs to produce this, just in terms of the resources. So this is why I think we need to start simple, so that we can actually build things that, I mean, that bring enough revenue to sustain the business.
Yeah,
Go ahead, Rose. I'll go next.
Okay. Yeah, I totally agree. I think one thing to call out is that, you know, although deep learning provides these really powerful methods, they're not always necessary. Sometimes it is better to go with a simpler, more cost-effective solution that will still give you just as much information as you would get otherwise. And I think one other thing to point out is this domain of remote sensing is quite different from natural imagery. So if we focus on the things within this domain that are different, that can kind of show us what sort of techniques we should be concentrating in. So for example, in remote sensing, we have an unbelievable amount of data over the surface of the Earth, but we don't have a lot of labels. So, you know, we try to think about what kind of techniques can we use that take advantage of data without sufficient labels. So things like unsupervised learning, self-supervised learning, semi-supervised learning, different things like that. And then maybe one other thing to call out is in the natural image domain, I think that there's some consensus that, you know, some of those problems are solved. But when you move over to these new domains like remote sensing, when your imagery looks so different, when things are more densely packed and objects are smaller, I wouldn't say that those are solved yet, and we definitely need people to be focusing on those issues.
So I just wanted to re-emphasize what both Rose and Grega said. And it's actually interesting because, you know, that's exactly our experience. I mean, you know, we produce different kind of different data products. The ones that we produce in for poverty mapping, for wealth asset estimates, and so on, they do use CNNs. On the agriculture side, and Rose, you're very familiar with this work. Actually, we found that random forest, you know, does just as well as deep learning. And by the way, you know, it actually it is much more scalable at the resolution and extent that we want to work at. So, you know, we you know, I think to the point that Grega was making, you have all these sophisticated tools, but part of the charm here is to be able to line up what tool you need for what problem you're trying to solve. Because if you get that wrong, then it's not just the economics that kind of set you back. It's also kind of the ability to reproduce, its ability to access talent, to continue improving the solutions, and so on. So, and that, I'll tell you, that was a surprise to me when you know, I first joined Atlas AI a year and a half ago. I thought that everything was CNNs, and it turns out, you know, quite a bit of it is, but for some of the key things that we do, random forest is just as good.
Maybe I can add a little bit of the methods we use in our work. And besides, you know, semi-supervised learning has been super effective, leveraging a lot of the existing frameworks and networks people have developed. But I would say a couple of other ideas that I found very useful. One is not a method, but it's really about what kind of data can you find to help you label things, and what other types of large-scale sensing information is available out there. So for example, for mapping distribution lines in cities, we found that photos from Google Street View can be used very effectively, and you can basically reconstruct a lot of the overhead lines from it and actually even get equipment in the lines and so on. So that ability to be somewhat of a data sleuth and accumulate different pieces of information, I think, is important. The other thing we found very useful is how do you deal with different image resolutions? So particularly as you try to do historical mapping of things, when you go back into the past, you know, if you're using DigiGlobe satellite imagery, that's high resolution, but it's not available all the way to the past. And we found that there you can use ideas from sequential Bayesian analysis or some kind of temporal models that know in the high resolution things exist, then the probability that it existed in the year before is higher, and so on and so forth. So with that, we used it in solar to map for about, right now our performance is, I think, around 85% of the panels. We can get the exact year it was installed on every rooftop. And the last piece, I think it's also very important, has been, then you have a massive mapping of information, particularly with this temporal change, It also changes the way you can do econometric analysis, particularly causal inferences about what factors drives adoptions or other things. In a conversation with Susan Atty, who's a faculty here at Stanford, an economist, and she's leading this revolution in economics around using machine learning in that context. She said something very interesting. Normally in economics, you need randomized trials because something akin to that, some type of experiment to infer causality. But if we can observe everything, then you know everything, so you don't need that randomization. So now what can you do? And we are talking with her about, for this solar project, you can try some new ideas and so on. So I think there's a lot of creative things you can do besides what Victoria, Rose, and Grega mentioned, which are amazing and super fun. I would really say it touches every bit of knowledge that I learned in stats as well. So it's a very interesting area.
So for us, ultimately what we want to do is produce forecasts for the amount of solar electricity that's going to be generated at ultimately every PV system on the planet, ultimately. And so that breaks down into several different problems. So one problem is, so never mind predicting the future, just can you map from an image of what the clouds look like to an estimate, hopefully a probabilistic estimate, for the amount of power you're going to get, say, in the middle of that image. And to folks who aren't familiar with this field, they might think that's fairly easy and fairly solved. Surely it's just, is there a cloud in the sky? If there is, then you're not going to get much sunlight on the surface. If there isn't, then great. It turns out it is a lot more complicated than that. Different cloud types do very different things to the passage of sunlight through the atmosphere. Water vapor attenuates the passage of sunlight, pollution does, all these fun things. So it's definitely not a trivial problem. And so far we've just made very early inroads into this, just training a simple convolutional neural net, taking a rectangle of satellite imagery and inferring what the PV yield would be in the center of that image. And that works fairly well. We're still playing with that. Then ultimately we want to be able to predict the future. So some folks, including some excellent undergraduate students that Sharon supervised, have done some awesome work here. And as other speakers have mentioned, one of the challenges here is lack of labeled data. So only a very small fraction of the Earth's surface has PV panels on it. So maybe we can do things like have a convolutional RNN, so a kind of sequence to sequence model where on the decoder side, you emit not just an estimate for PV yield, but also an estimate for what the pixel intensity might be in the center of the image. So then you can train everywhere you have satellite imagery, not just where you have PV. And then my real sort of geeky wet dream is that we ultimately use machine learning to completely reconstruct the 3D structure of the atmosphere and then use techniques that are just starting to become tractable computationally from computer vision, well, not computer vision, from 3D graphics. So specifically path tracing, which traces the path of rays of light through scenes, and maybe we can do that for the whole atmosphere. And that might give us a mechanism to combine lots of different data sources. So there are all sorts of fun satellites that give us like the vertical profile of clouds, and there's all sorts of priors that we can use. So there's lots of fun to be had there. And maybe the last note to say is that we're really excited about enabling the community to work on this. So we've been saying this for ages and haven't done it yet, but we are planning to redistribute some of this data in a completely open fashion, in a cloud-friendly form, so that anyone who wants to can have a go at solving some of these problems.
That's amazing.
Before we go on, I just want to make another comment, sorry.
Please.
Which I think is important. What I see, I mean, in the remote sensing and machine learning, you have two worlds, right? On one side, you have the remote sensing experts who are used to work with so-called vegetation indices and things like that, and they really look at that images for all the time, and that's their work. On the other side, you have the machine learning experts who want to be really pure with it, and they take the sensor data and they want to forget all about the indices and they just want to work with that. And I mean, I think what is important is that we try to use the knowledge of the both world, like by simply using some of the vegetation indices, which are there for decades already, and throwing them in the neural network. You can simplify the CNN by a couple of layers, therefore making the system much cheaper and much faster. And one other thing that we shouldn't forget is that with remote sensing data, you're often modeling the real world, which means that, first of all, for the labels, you can often take the labels from, I don't know, administrative sources like property registers and things like that, which exist around the world, but also that you can then incorporate some physical models in your machine learning models as well, so that, I mean, simply you make it faster or make it better in terms of quality.
Cool, thank you. So now shifting focus a little bit from technical to more, I suppose, client or user-facing work that all of you do. What stakeholders do you work with in deploying your work? And are there challenges involved in making sure it's ultimately impactful? And this might tie in with an audience question. What advice can you give us to build collaborations like the one Ron mentioned, where there was a need and two students used the tools to meet those needs for solar panel mapping? And perhaps starting with Ron there.
Hi, Sharon. So for our electricity work, we work with a broad ecosystem of companies, other researchers, so ranging from utilities to, you know, EV companies like Tesla, battery companies like Sonnen, various startups that are doing new devices for energy systems, and policymakers. So we collaborate very closely with the California Energy Commission. We have worked with the PUC in the past. And I think there are two key ways to engage with this broad audience. I think one is by really talking to them and finding out what are decision problems they have, mapping those problems into which ones maybe I can address, and starting there. The other one that has been very effective has been just to publish your results openly, including whatever you mapped and the data that's been made available. Due to some privacy regulations, the university didn't approve us to publish every individual solar panel location, but we did publish lots of summary statistics. We have created some simple mechanisms for people to access some of that information, and that also opened lots of doors there. So I think those are two very simple ways to get things going.
Does anyone want to follow up on perhaps challenges in working with stakeholders to make sure your work is impactful?
Maybe.
I can maybe, no, sorry, go ahead.
I was just going to offer up some of our experiences, you know, again, working in Africa. And you know, it's a hard road to travel because, you know, we generate the data, but, you know, we don't want it to be like put in data jail or something. You know, we want it to be available to those people that need it the most. So how do you reach those people if you're a company here in Palo Alto and your constituency is that far away? So for us, you know, this kind of ecosystem of partners, you know, aspect is really fundamental if we're going to have the impact that we want to have. One of the ways that we've done that is by partnering, in our particular case, with an organization called AGRA in Africa. It's the Alliance for Green Revolution in Africa, and they have a kind of, you know, a ground roots organization in about 13 countries. So we work with them to, you know, inform what data is available and how to push it out there. But what we're also finding, especially in the continent, is that there is really a lack of a data kind of infrastructure. Without that, it's really hard to have a consistent kind of distribution channel, if you like, for the data, both to the policymakers as well as the consumers. In our case, it will be all the way from the Minister of Agriculture to the smallholder farmer. But what we also see is an increasing kind of desire and investment on behalf of those governments to create kind of sustainable. In the case of Kenya, for example, Calro is putting together, with help from the World Bank and Mercy Corps and others, a central kind of data lake where people can both share data, training data and validation data, as well as resulting kind of data products. And that would be a thing, one cool way that we have to push the the results out there. Plus, honestly, for us, and I suspect for many other colleagues here, getting access to training data that we don't have to go collect ourselves, that accelerates you so much. So it's access to kind of to data stakeholders is both on the kind of intake and the outtake of the work that that we do.
And just to double on that, I think that the major challenge is that the clients, they have a completely unrealistic expectations in terms of that they believe that you'll come with results that are 100% accurate. So they don't get this, like, I don't know, 95% or 90% accuracy. They simply don't understand it. And then on the other side, they usually don't provide any label data at all, right? I mean, so they expect that you will simply use the satellite data and then come up with something what they are after. I mean, so this is the problem, is that people don't understand the challenges of the machine learning. And probably what we need to do is really to raise awareness of what are also limitations, right? That you cannot do everything. And I just want to double on Ram that I think what is really important is that when we are sharing the results, we don't share just the, stories and some nice pictures, but that we really share the validation and training data, so that someone who is reading the paper can actually repeat the exercise that you did, so that they can learn from it and that they can obviously validate that you have done, right? I think that at the moment there is too much storytelling in this world, in the scientific world as well.
So we definitely have upcoming challenges in having impact. In fact, I think this is probably the thing that keeps me up most at night is, let's say we solve the technical problem. So let's say a team of people in the audience today comes up with a great way to do solar forecasting by the end of the week. Brilliant. That's amazing progress, but we are by no means done. The climate hasn't yet noticed that great piece of research. We then have to persuade electricity grid operators to use those forecasts and to trust them. And that will likely take years. And perhaps one of the surprising things here is that electricity grids are still very human things. So certainly here in the UK, the control room is still very much full of humans, and they send instructions not to computers at power stations, but to other humans at power stations. And it's them ultimately making the decisions. They have lots of decision support tools, but it's the humans making the decisions. So ultimately the task is to convince the humans in the control room that your forecasts are going to help them and can be trusted. And that will probably take several years, even after we've done the majority of the technical work.
Great, thank you everyone. What, I think following from what Jack just said, what trends do you all see in remote sensing that's relevant to climate change? Perhaps in your work, how does your work tie to tackling climate change? I think Jack's was pretty obvious, but other folks can also chime in.
Yeah, I can chime in here. I think that industries are starting to care quite a bit more about sustainability practices within their supply chains, especially since remote sensing data is available and makes these things transparent. So I think that there's been a trend in industry to basically alleviate some of this pressure that is coming from transparency of remote sensing by making sure that their supply chains are more sustainable. So something that we can do at Descartes Labs is, be that monitoring factor of, say, a company agrees to some task or program, and they have to show that, you know, they're not contributing to deforestation around their fields. So we might be able to go in and then show whether or not they're complying with these regulations. I think there's a huge opportunity for remote sensing to serve as this kind of regulation compliance type of, to wear that kind of hat.
And also, I think in our case, especially in the agriculture kind of area, because the insights and the data sets that we generate are so kind of, you know, they're so accurate and they're so kind of localized. You know, they can be if you look at them over a period of years, they can start helping you how to prepare for climate shocks. So, for example, you know, we have you know, maize production estimates for the last 4 years for Kenya, and you can see how drought has affected production in various areas. Every time this you know, this happens, it's an opportunity to understand what areas would be most hit. And that also gives you an opportunity then to plan. So when the next drought happens, for example, you know, the crop doesn't get decimated in this area. There's some areas that are, you know, more susceptible than others. So I think in general, you know, the more data you have, the better position you're in order to be able to anticipate and prepare for what we call climate adaptation, really. I mean, this is not an area that Atlas AI has worked in specifically, but you can see how the work that we've done almost as a byproduct can help, you know, comprehend how, you know, countries like Kenya could begin to plan as the climate changes, so that, you know, the impact is mitigated.
I think on the kind of electricity side, there is 2 areas that come to my mind besides what Jack mentioned that I think is very critical as well. One area is the ability to use the data we have so far to learn how can we enable, you know, the deployment solar, wind, and all these new technologies in other countries. I think it is doing these plans for India and China. I've met with, you know, officials from different countries, and it's a big challenge today. And even just gathering their own data for their countries is a big effort. So if we can accelerate that, that's already a huge impact. The other area I feel that will be very important and is coming up is really to provide risk assessments of how the different pieces of the electricity sector will be affected by the ongoing changes in weather patterns and so on. Weather is a huge input into the system. Estimating these risks is a completely new science. People have not done this before in electricity. And it's kind of an intersection of infrastructure and environmental science and data. For example, we were talking to one faculty here at Stanford about, she told me, well, you have all these maps of these infrastructure. I kind of analyze how forest fires spread. Can we use that to compute risk maps for California that would then aid the utilities to better do, you know, whatever power shutoffs they need to do and things like that. So I think those 2 areas are areas that I feel we can have an immediate impact.
Fantastic. We can move on. So what are the legal and privacy implications of your work? How often do you think about this, and in what context? And tying in with an audience question, what about the availability of the output of remote sensing pipelines? Some of these insights are currently proprietary.
Maybe I will start off with this question because we went over a 1-year-long process to make all the data we generated public. And much like what me and my students do, you know, we produce what we want to produce. We put it on a website, and it was there until the process started, and then the university asked us to take stuff down. Then there came federal government mandates about what can you share internationally in terms of methods of analysis on this type of remote sensing. My personal opinion is there needs to be a real, true democracy of data. I think, before there was a confusion in my mind between the anarchy of data and the democracy. I think in a democracy, you need to have some organizations that can serve as stewards of what are fair uses of data, what's safe to do, in what context, and that also does not slow down the process that we have today that is free and open a lot. I think this is a very essential. We haven't figured out how to do that yet. In practice, we find the privacy issues are big, even when people want to and are willing to share their information. So there's a lot of issues that need to be tackled there.
So, one of the, we had a similar experience, Raman. We're, of course, we're a company, so nobody can tell us to take data down, but trying to figure out what the right balance is between creating public goods, so to speak, and creating, in our case, data products that will keep our company, going is an ongoing conversation. I don't think there's a formula that describes that. But to your point, Sharon, around kind of privacy, it kind of comes in a variety of forms, and again, it's one of these problems that I don't think has a precise solution. If you look, for example, even at our data sets, a lot of the work that we've done on the kind of the poverty side is based on LSMS data from the World Bank, which is jittered, so that the privacy of folks is preserved. So then the question is, well, how does that impact the accuracy at the other end? So we've been doing some interesting work to see, what is the difference between jittered and unjittered data. So, and that's something that I think is essential for us to understand as we, really look into very private data that households, in this case, offer to the World Bank. At the other end, if you look at and these are unexpected things that, again, I would never have imagined when we got started. As you create really high resolution predictions about productivity of a farmer or a field, you would have thought that this is all good, right? It's all good because it tells the farmer what he's doing. It tells the district level what they're doing. It's all good. However, imagine, if land tenure is an issue, if land tenure is tentative in a country, two things could happen. If I'm really good at producing and my land is highly desirable, maybe somebody will come and take it from me. If on the other hand, I'm not very good at land that I'm leasing from somebody, maybe they'll kick me out because I don't produce as much as the next person. So these are very unexpected kind of privacy aspects that, I had us even scratching our heads at some point, how much of that data really we would share with whom to make sure that people's livelihoods are not impacted, which is precisely the opposite of what we're trying to do. So I think it's fascinating. And unfortunately, I don't think there are any easy solutions. I think in each case, somehow, we have to come up with an answer that respects privacy and fundamentally, exhibits, I think, integrity on everybody's part as the guardian, as a technician of data, right? Like we all are.
Lovely. As we near the end of the hour, as a final question, which addresses several questions from the audience, how can audience members get started working on remote sensing? What are accessible paths to contributing that are also impactful?
I would suggest to go to elearn.sentinelhub.com, where they will find quite some material to start with. And then you can just start working.
I have another suggestion. They could also contact Sharon that conducts this amazing AI for climate change group here at Stanford, and gets so many students working on so many different problems and connecting so many people. I think it's an amazing opportunity to learn these techniques from Andrew, Sharon, and then use them in problems that are relevant to me or Jack. So I guess if you mass mail her, maybe she'll be a little upset at me, but I think at Stanford we'll love to have more and more help, right, Sharon?
CC Rom.
Yeah, I guess, and I wish we'd already had this ready, but we're hoping to release a data set of EU Metsat satellite imagery in a cloud-friendly form and solar PV data for the UK, hopefully quite soon. I mean, this speaks to the problem about legal questions, is that for the PV data, the company has said, yeah, sure, we're fine to share the data publicly, but it's just taken months backwards and forwards with their lawyer figuring out the exact terms of that sharing. So it will be coming soon. So yes, please ping me if you're interested.
I just wanted to add one little thing. Also, a lot of our students found the Decartes Lab platform amazingly helpful, and they're also very open to letting us use this for different experiments. So I know Rose is going to talk about it, but maybe coming from a user might be nice. So just that.
Yeah, I can hop in there. At Descartes Labs, we have this platform that scientists can come in and use. The main purpose of that is to get rid of all the data processing and the headache that comes with that and get into your science more quickly. So we do have an impact science program that opens up 2 times a year, and I would encourage people to apply to that so that you can start using the platform.
And just to double up what I said on the chat, a couple of weeks ago, we open sourced our asset wealth data at full resolution. Anybody can go to our website, sign up, and download the data set and also play on the platform. And the other thing I just wanted to share with you, we've done all this work, and we've not paid a penny for any satellite imagery. I mean, it's all Landsat and Sentinel-2. So this is truly surprising. So all these incredible resources are available to anyone to get started without any cash outlay. So there are plenty of resources out there.
Lovely. Well, thank you so much, everyone. This was a fantastic fireside chat with perhaps virtual fires. So thank you so much. And I will now be handing it off to Priya for closing remarks.
Yeah, awesome. Thanks, Sharon, and thanks to all the panelists. That was a really enlightening and thoughtful discussion, and I really enjoyed that. So just to close out the workshop, so this is actually the end of the 5-day workshop, which flew by really, and yeah, featured some really amazing sessions on both methods of machine learning that have applicability in climate change mitigation and adaptation, as well as the applications themselves. And I think a lot of the themes echoed throughout the workshops are really summarized very nicely by that last panel about, methods, complicated methods necessarily potentially filling some gaps, but more simple methods being applicable in other places, the need to work with stakeholders very closely, the need for collaboration, and then a lot of those other themes. So yeah, I can't think of a better way to have ended the workshop than with that session. So I'd also, in addition to the speakers of this session and the previous sessions, love to thank the other organizers of this, the program committee who helped review submissions for the workshop, and the iClear conference through which this is hosted, and our sponsors, Microsoft and DeepMind. Without all of these people coming together, this definitely would not have been possible, even and especially in the virtual format. So thank you so much. And thank you also to all the participants. We had some really engaging questions, really engaging conversations going on in the Zoom chat today and earlier in the week. And so thank you for kind of uplifting the discussion there. That was really wonderful. So this workshop is run through a broader initiative called Climate Change AI, which seeks to facilitate meaningful work at the intersection of climate change and machine learning. So among other things, we wrote a 100-page paper detailing ways in which machine learning can be applied with high leverage to problems of climate change. That paper, some summaries of it, and accompanying resources are on our website. And there are also a lot of different opportunities to sort of continue the conversations that you've been having with speakers, with other participants in a digital format. So one of this is the Climate Change AI discussion forum. This is a place where you can post maybe resources that you've been using. So there are a number of tools and resources, for example, that got posted in the Zoom chat today. If you have others that you use in your own research that you think would be really useful to the community, this is somewhere to post about it. Or if you're looking for collaborations, if you have project ideas, if you have questions, no question is silly, right? We had tutorials on climate change and machine learning earlier this week, and audience members came up with very intelligent questions and very insightful ones. And so this is also a place to continue asking those kinds of questions. So I would definitely encourage you to check it out and sign up. Again, forum.climatechange.ai. And then additionally, we have a once monthly newsletter, which for those of you who registered for Zoom, you will have seen a question, do you want to sign up for the newsletter? And so this has kind of a roundup of calls for submissions to various workshops, funding you can apply for, projects or courses you can plug into, readings that we found particularly interesting at the intersection of machine learning and climate change, as well as jobs that you can apply for. So if you want to receive this newsletter, sign up on our website, or additionally, if you'd like to contribute to this newsletter, just email us at info@climatechange.ai, and we can make sure that your information gets disseminated to the community. So with that, I'd like to thank everyone once again. That was, again, just a fantastic week, and I'm really happy that we all got to come together in this digital format to really have these incredible and insightful conversations about work at this intersection. So with that, wishing everyone a great rest of the week and weekend, and hope to see you around on the various digital platforms fairly soon. Thank you.